So today's class, we're looking at topic 5, how structures fail. So if there's a great enough force acting on a structure, it will begin to fail. Even if there's small forces, and those small forces, if they're acting in a vulnerable place, it can cause damage, which can eventually cause a structure to fail. So the first example we're looking at are levers. Levers create large forces. So we have frame structures. If they're made of long, rigid lengths of lumber or steel, they can fail when the force is applied to them. Such failures can result from the force created by the action of a lever. So recall that a lever, it's a device that can change the amount of force needed to move an object. So here, if we look at this lever here, this like crowbar, the fulcrum is here, effort force is what we would apply here, the load force then therefore would move upwards. So some types of levers, they consist of a long arm that rests on a pivot, which is also called the fulcrum. So when effort is applied as an external force to the lever, a large enough force is created to lift a load. So in this example, we have the crowbar, which is used to lift a rock. In this example, we have this flagpole acting like a lever and how its structure can fail. So think of like strong winds. So strong winds can exert an external force, and that can start to bend the frame structure of a flagpole. Even a slight bend can exert a large force on one side of the flagpole's base. So then this base here is going to start acting like a lever. As the external forces are pushing down against one side of the base, the other side pushes up against the load of the flagpole. So we can see that happening here. And then eventually the bolts that are holding down the frame, they're going to weaken. The frame structure to the base is going to weaken. The flagpole can then fall over. Strong winds can also produce other forces that can result in structural failure. Here in this example, we have winds in a tornado. Those winds are going to produce twisting, bending, and compression forces, so causing lots and lots of damage. Next is how materials can fail. So external forces can cause internal forces in a structure. And each type of internal force can then cause certain types of damage. So if we look at shear, the shear force, so solid materials, they're never perfectly uniform. There's always some microscopic cracks or weaknesses. And when that solid material is compressed, that crack can enlarge, it can then break apart. One section may shear, meaning like slide over another section along that weakness. So here, there's a shear failure happening here under compression. Then the weight of a building can compress the soil, causing the soil to shear or start to slip sideways. And then the ground beneath the building can also sink. Therefore, the building can tilt or collapse. So here in this diagram, even if the ground beneath the building was uniform when the building was constructed, shear damage can still can occur. And in this example, there was an earthquake which caused this damage. So materials can also fail if there's bend or buckle. So if you, for example, put pressure on a metal can, the thin metal will start to fold, the can will buckle, meaning it'll give way under that compressive force that you're applying. Same thing if you have a piece of paper, the same thing happens to a piece of paper when you push the ends together. So all thin panels, they tend to bend and buckle when they are compressed. So compression forces, they cause material to bend on the inside of the curve and then pull and snap on the outside of the curve. Shell structures that use thin panels to support their entire load. So for example, boats and aircraft, they're usually reinforced to prevent buckling. So some things to think about are like, how can an engineer design buildings so they don't bend or buckle during an earthquake. These are some common designs: a rib, stringers, stringers and ribs. These are common designs that are used to reinforce structures in order to prevent shear, bend, buckle, and twist failure. The stringers and ribs are used to reinforce large vessels like cargo ships, aircraft, rockets, and usually they are hidden beneath like an exterior skin, so they're not easy to see. That'd be for like aesthetics. Making use of stress. So materials will snap, twist, buckle, bend, and shear when they fail. But these same behaviors can also be used for good. They can be put to good use. So for example, buckling. So car bumpers that we see in the front and sheet metal can be designed to buckle in a collision. And basically as the metal deforms, it will absorb some of the energy of the impact. So the car, it may get badly damaged, but the people inside are less likely to be seriously hurt. Another example, blades of grass on a sports field, they will buckle as athletes land on them, so they will absorb some of the energy of the impact. Certain kinds of panels, like the bellows in an accordion, the flaps on a cardboard box, they are also designed to buckle in specific places when you press on them. Also, we'll talk again about margin of safety. We talked about that previously. Car designers, they do increase the margin of safety for vehicles by using principles of material failure. So like using those car bumpers and certain sheet metals. For shear, making use of stress, in a boat's outboard motor, the propeller is held to the drive shaft with a shear pin. If that propeller becomes tangled in weeds, the shear pin is designed to break, therefore allowing the motor and the gears to spin freely instead of getting damaged. In a car, the clutch and automatic transmission of a car are designed so that shear forces will allow forces to slip past each other, so speeding up or slowing down gradually until they're moving at the same speed. That will produce a smoother ride than connecting the engine directly to the wheels. For twist, thinking of like cotton and wool, so spinning wheels, they will twist cotton or wool fibers tightly so that they lock together. Then that twisted yarn is way stronger than just a bundle of straight fibers, and it's long enough to knit or weave into a cloth. But if the fibers are twisted too much, they can tangle and shorten unless you keep pulling on them. So that's one way to make like stretchy fabrics. So controlled twisting, like turning hair into braids, string into ropes, and wires into cables. Next is metal fatigue. Metal fatigue is the weakening of metal because of stress, and it will result in like an accumulation of small cracks. So metals will weaken when they're bent or twisted over and over again. Basically what's happening is the particles are changing. The arrangement of the particles is changing. And then when particles move apart, the forces that's holding them together, they become weaker. And then if enough particles are affected, then you'll see the small cracks developing. And then that material may eventually fail under only like a small stress. And if it was new, it would easily have resisted it. But because of that, over and over again, bending and twisting, it's going to fail under that. It's still a problem even in lightweight, flexible structures in aircraft.